My name is Rania, and in this video I'll be explaining the Leucine Zipper and alpha-helices for Module 1 Discussion 2 presentation. So for prompt 1, what principles are involved in holding two alpha-helices together? So generally, two alpha-helices can be held together with disulfide bonds, ionic bonds, hydrogen bonds, by hydrophobic interactions or electrostatic interactions. And in this picture here on the left is from our textbook. It's a drawing of the alpha-helix, which is a rod-like structure in a spiral or ribbon depiction as shown here in picture A, with tightly coiled backbone as shown in picture D. The side chains of the amino acids composing the structure extend outward in a helical array, as we can see here in picture C, as it shows an end view of the coiled backbone as the inside of the helix and the side chains projecting outward. Picture B here is also showing a side view of a ball and stick version that is showing hydrogen bonding between the amine and carbonyl groups right here. And this takes us into the next question asked, what principles are involved in holding lysine and glutamate together? So in this case, it is the hydrophobic interaction that's holding the two leucine molecules, an electrostatic interaction between lysine and glutamate right here. And hydrophobic interaction is between the lysine and lysine. What principles are behind hydrophobic interactions? So according to the textbook, the definition of hydrophobic interactions is the process in which nonpolar molecules in aqueous solutions are driven together because of the resulting increase in entropy of water molecules, which is basically it increases stability. Hydrophobic interaction forms spontaneously. There is no input of energy that's required because, as mentioned, when they form, the entropy of water increases. And all of this is supported by the second law of thermodynamics, which states that the total entropy of a system and its surroundings always increases in a spontaneous process. What principles are behind the electrostatic interactions? So again, according to the textbook, the definition of electrostatic interactions is a weak interaction between ions having opposite charges, also called ionic bond or salt bridges. And they usually take place between atoms bearing a completely negative charge and a completely positive charge. And interestingly, water weakens electrostatic interactions due to its polar characteristics, but electrostatic interactions reach its maximum state in an uncharged environment. Suggest one possible residue that could replace leucine. So one possible residue that could replace leucine is isoleucine right here. If we look at both molecules, we would conclude that both have equal number of carbon atoms and both have the same molecular mass. So both are likely to exert the same extent of hydrophobic interactions. Therefore, replacement with isoleucine is most likely to function as efficiently as leucine for maintaining the hydrophobic core. And this takes us into the next question. What is one possible residue that would destabilize the core? So any hydrophilic residue could destabilize the core by breaking the hydrophobic interaction present. As the surrounding medium is aqueous, the hydrophilic amino acids would prefer to be exposed to the medium rather than being clubbed to each other. So an example of amino acids that would do so includes serine, threonine, aspartate, and a couple of others that can destabilize the core. So I have here serine and aspartate together because both of them are polar and negatively charged, and threonine as polar and neutral. And this takes us into the second prompt, which is what other amino acid pair whose side chains could interact in a similar manner to lysine and glutamate. So any pair consisting of one acidic and one basic amino acid would interact in such a manner. So I have here aspartate and arginine, aspartate being the acidic amino acid and arginine being the basic amino acid. And this concludes my video. Thank you.